Hi, I'm Tom Sherlock. I'm giving a talk this morning about planetary image processing using the Wolfram language, and it's how to import, stack, and statistically process data coming from a telescope when imaging planets. Do we have any professional scientists or astronomers here? Only a few? Well, don't worry, I'm not one either. I'm a user interface developer here at Wolfram Research. But anyway, today I'm not going to be speaking about software development. I'm going to be speaking about features that I've developed in Mathematica. I'm going to be speaking about my hobby, which is astronomy, and in particular astrophotography. And one of the things that I've been doing a bit over the last year and some time before then is taking pictures of planets. And this is a little different than what people normally think of as astrophotography, and it requires a different sort of data reduction. And so I thought I'd go through some of the ways that Mathematica and the Wolfram language helped me out in this. So let's get started here. And I'm gonna try to time this so I have time for questions at the end. So that's the way it's gonna work. Anyway, the abstract is basically a summary here. And the Wolfram language is a really great platform for doing stuff related to astronomy because it contains a great deal of astronomical data. And it also contains very powerful image processing and data reduction features, which in particular come in handy when doing this sort of work. So I'm going to talk about some of these things and show how I can take a series of really fuzzy, grainy images and get something that looks kind of reasonable. Now, when people normally think of astrophotography, they think of a little different sort of operation. And I'm not gonna talk about this in depth because I've talked about it in different talks before. And I'm going to just describe how people normally do astrophotography. And they're typically, pictures of astronomical objects are typically imaged from dozens of fairly long exposures, 1 to 5 minutes typically, to maximize the signal to noise ratio. The issue with imaging dim objects is trying to separate the signal from the noise. So everything that you do with like normal astrophotography is trying to maximize the signal. And so for that reason, you need a fairly long exposure, which therefore requires that your telescope be accurately aligned with the Earth's polar axis. And then on top of that, you need to use some sort of guiding operation, either manually, like they did in the old days, or basically closed loop guiding, where you have an additional telescope on top of your telescope pointing towards a star, which picks up variations in the position of the star, which is due to errors in the gear train on your drive. And then it feeds correction pulses back to the drive so you can stay locked onto an object for a fairly long time. If you want to take a picture of a larger object, for instance, the Andromeda Galaxy, you have to do, depending on what sort of equipment you have, you typically have to do that in pieces and make a mosaic. And one of the more tedious things that people don't realize is if you want to get really good data, you have to take not just images of the object, which are the light frames, but you have to take a series of other frames which measure the noise that's present in your CCD camera. And so these encompass things like dark frames, flat frames, which help you subtract off light fall off and dust on your CCD, bias frames, which just measure the readout noise of your CCD, and dark flat frames. But we're not going to talk about that today. We're going to talk about planetary astrophotography. And the big difference between diffuse object astrophotography and astrophotography of solar system objects is the planets are much, much smaller and brighter than nebula clusters and galaxies. And the largest and brightest solar system objects you might image, the sun and the moon, are still small compared to some diffuse objects. And to give you an example of this, the angular diameter of the moon is about half a degree, 29.555 minutes. But the Andromeda Galaxy, which is one of the brightest galaxies in the sky besides the Milky Way, is over 3 degrees. So the moon is 1/6 the size of the Andromeda Galaxy. The Andromeda Galaxy, you can actually see it if you go out on a fairly dark night and just look in the right spot of the sky, and you'll see a blur there, which was in ancient times was known as kind of a little cloud, but it was actually the core of the galaxy. In order to image the entire galaxy, you have to take a long exposure. So, so the differences with solar system objects, instead of a dozen exposures, you typically take hundreds or thousands of exposures, and each of them is very short. So the fact that you're taking a very short exposure kind of negates the effect of the planet moving around because of errors in your gear train. For the same reason, it doesn't require careful alignment of the telescope or manual or closed-loop guiding. The drift effects can be canceled out by software operations, and I'll show you how that's done. Since the objects are typically small, there's no need to mosaic, except in cases like where you're taking wide-angle pictures of the moon, then you will still have to do that. And noise, again, is not really a big problem because the images, the large number of images tends to compensate for this problem. And the sensor that you use, unlike in the case of diffuse object astrophotography, doesn't generally need to be cooled. The camera I have, which I take pictures of dim objects, has a thermoelectric cooling system on it. And more expensive cameras have more sophisticated systems where you can actually pump water through the camera. So you can do quite a lot with just a webcam. This is a Logitech QuickCam 3000 that I've repurposed for my hobby here. And I just adapted it like this, so it'll fit in the back of my telescope. You don't even have to do that. I've also taken semi-okay pictures by just holding my iPhone up to the eyepiece of the telescope and just kind of having it swim around there, but that's not that big of a problem because you track these things and you're going to compensate for it. So let me show you some of the techniques I used. So there's a workflow. The first part, of course, is the collecting the images, and this is the part that's done with heavy, expensive, fragile equipment and computers, all done in near pitch darkness. But after you get done with that part, you do the software workflow, which is importing the images. Then you want to sort them out because you're going to get some clinker images, and you have to have a systematic way of finding bad images. Now, with a short number of exposures, you can just find which pictures are fuzzy or bad or smeared and just eliminate them. But for planetary, when you're dealing with thousands of images, you have to have some sort of systematic way. So that requires some image processing and data processing. Then you need to align the images. Stacking the images is a statistical process which smears out the noise and extracts the signal. And then typically you have to stretch the images so that the data is more visible, and then do final processing, which includes sharpening and deconvolution. And the Wolfram language helps you do all these things very efficiently. So let's talk about importing images. One of the powerful features of the Wolfram language is it's easy to get data into it. And lots of different things. For instance, here I'm just enumerating files in a directory, and I'm going to import some Jupiter images. Now, these weren't actually taken of in the same sequence. They just had these images lying around. So if they were in the same sequence, they would look more like these two guys here. But I just wanted to show how you can easily bring in ping images right into Mathematica. If you're familiar with astrophotography and astronomy in general, you probably will be more used to this format, the FITS file format, which is more important for scientific work because it contains a lot more data, and it contains scientific data that you will need, for instance, information about the camera and the exposure and calibration and stuff. And we can bring that stuff right into Mathematica too. However, it's a little bit different because it comes in as an association. So I'm going to have to untangle the stuff, but that's easy to do. So I'll bring in some fit images. And there you can see my fit sequence. Of course, you can't see anything unless you have a really good eye here because Jupiter is pretty dim there. But if you just want to see what they look like, you can apply image adjust to this list. And this will give us a quick idea of what we got. And so you can see the images here. I don't know why this one has a bad exposure, but it doesn't really matter because since we take so many images, we're going to kind of identify clinkers and filter them out, and everything kind of smooths out. So another way you might want to collect data is with video. And this is probably the simplest way because a video camera, like the one I showed you, you can just plug in and capture video from it. And this also has the advantage is that it collects very rapidly collects a large number of very short exposures, which is good because, as I said, that will negate the effects of periodic error in your gear train. So I'm going to import a video file here. This is just an AVI file, and it's generally best to import uncompressed video. So that's the path, and then this is, a Mac doesn't normally deal with AVI, so it converts it to QuickTime. And this is just a list of all the frames. It's a little dumb, but you'll see later on that this is kind of a useful thing. This is just a list of all the frames, a short form of it. So this sequence was 1,200 frames. And let's just bring in the first 10 frames as kind of a short image sequence. So it just pulled that in. And now we can just see the Jupiter images off the video. And there's one of them. And here I can just flip through these. And you can see that even though the exposure is short, Jupiter's still dancing around a little bit. And that's because of atmospheric instability. And it's hard to compensate for that. We're going to try aligning the images, but still, after you align them, you'll still see some distortion. So I'm working on that for next year's talk. So then after you get the images into Mathematica, you need to cull them. And basically, you filter out the bad ones. And so this comes into the question of what's a bad image. And this is actually not a trivial thing. There's a lot of methods for image quality assessment and a lot of literature on that. And generally, it's assessment where you give it a perfect image, and then you give it a corrupted image, and then you determine the quality based on comparing the two. But that's not what we have here. This is called blind image quality assessment. So basically looking at an image without any reference image and determining what the quality is. So the good news is we don't need anything super accurate. We just need to be able to determine what the relative quality of the images are. So for that, I like to use acutance, which is a vector field by taking the gradient over the image intensity as a function of its position in the image. And so we can easily calculate that in Mathematica by just taking the mean of a gradient filter on the image and flattening it out and just taking the mean of that data. So if we do that, I'm not going to calculate this because we're running a little short here. If you sort the images by the acutance, and you can easily do that with sort by, and then you do a list plot by applying acutance to the sorted image sequence, you'll see that the quality of the images varies. There's some crummy ones down here and some fairly good ones. And there's different ways you can measure acutance, and different packages, commercial packages have lets you choose the algorithm, and it doesn't really change the shape of this curve that much. It might shift it up and down. You can use the Sobel edge filtering to do that, but basically all we're really interested here is the relative accuracy, So what I then do is I figure how many I'm going to eliminate. So I'm going to cull about 20%, and then I will take my best frames are everything but those 20%. So take largest by acutance of the frame count. So if I do that, then we need to align the images. So the alignment is also done using image processing techniques. For instance, here's the best frame in our sequence. And you can see it right there. Still doesn't look that great, but that's the best we have. And the way I align them is normally I could use the alignment, image processing alignment functions built into Mathematica, but those key off of features. And you can see we don't really have too many features here. Really, the big feature we have is the planetary disk. So the best thing we can do with data of this quality is to just find the center of the disk. And that's easy to do because we can binarize the image and then do component measurements on it, and that will determine what the and that will give us the center of the image. You can see I've drawn a disk around Jupiter, and the center of the disk is the center of the image. So then, given that, I can write a little function. And here, this uses parallel processing capabilities of Mathematica. It does, so here it's morphologically binarizing each images after adjusting it. It does component measurements to determine the centroid. And then it does a parallel map on the center points. For each image, it does an image pad on it, and that shifts it to a target position. And the target position I'm picking is the center of the frame. The target x and y equals image dimensions of the best frame divided by 2. And then so the aligned frames are aligned planetary images. And this is all in the notebook that you can download. So once I do that, I get a series of images. You can see that Jupiter here has been shifted to the center of the frame. And it's not jumping around a lot as much, but you can still see it's kind of moving around in size and shape. And right now with the techniques I'm using, I can't really get around that, but that's kind of okay because it all averages out in the end. As I said, if you want, you can do further alignment using the alignment functions. And if you have very high quality images, you can further do that. Should have divided this up into more slides. So you can use image align, but that works best if you have very visible planetary features. Okay, so after you get the images aligned, then it's actually pretty simple. So what I do is I basically just convert them to data and just take a mean or a median of all the images. So that basically, since they're all stacked on top of each other, you can imagine the image stack as a several arrays, a bunch of arrays, and each column, a column of pixels, you're taking the mean or the median of that. And I'm not going to do that right now because it takes a few minutes and we're running out of time, but this is the result here. And then you need to stretch it. And the reason for that is astronomical images quite often concentrate the data into just a small fraction of the range of values that could be. So here you can see the RGB channels are all concentrated in the range 0 to 0.4. So we can easily stretch this, and this will bring up the image. So now you can see a lot more color detail on the planet. And then the final thing you need to do is you need to do some sort of image processing to remove the fuzziness. And fuzziness is generally described by something called a point spread function. And for some images, and I've talked about this in earlier talks, it's possible to estimate the point spread function by just examining the image. But we can't really do that now. We could do that if there were stars in the image that were fairly distinct, and then we could pick them out and then figure out how they deviated from a point. But we can't do that right now because we don't have any stars in the image, so we're going to just guess. And a good guess is a Gaussian matrix. And you can see the point spread function kind of looks like this. So this would be a star in the center, which has been blurred out. And to see what that looks like a little more clearly, it's something that looks like this. So then we need to assume that the image is the convolution of this function with the real image. And so we can use our image deconvolution functionality to remove this. And Wiener deconvolution is a spectral deconvolution method, and it tends to be pretty good because one problem with deconvolution methods is they tend to introduce artifacts. And so that's our final image, and you can start seeing some details, cloud structures on the planet. And this is not bad considering how bad the initial images were. You can also do more sophisticated techniques, like one technique which is favored in astronomy is something called maximum entropy deconvolution. And this is an iterative method, and this is basically came out of radio astronomy, but it works good for visible images too. I'm not going to go into this too carefully, but this is based on some NASA code, and you can look at this later. The good thing about this is it doesn't introduce too many artifacts, and it converges rather slowly, so you can see what you're getting pretty quick, pretty generally. Now, one problem with dealing with a large number of images is you tend to run out of memory, especially if you're dealing with thousands and thousands of frames. So a smart way to do this is to process things in chunks. And the Wolfram language easily lets you do that because you can take the frame list that we saw before, you can partition it into chunks of 32 frames, and then stack each one of those chunks, and then stack the final list. This takes a little bit longer, but you don't run out of memory and your computer doesn't crash, which is always an advantage. And so here's some quick examples. That's the scope I used to take all these pictures. It's not a big scope. And if I import the stuff, I'm going to show you this. I'm going to close this down. And so here's a series of frames. This is just a few of the frames, but you can see one of the artifacts. This is not an artifact on the planet, but that's an artifact on my CCD camera. You can see that staying still. It's a dust blob, enemy of astrophotographers the world over. And so then if I stack that, and I'm just going to quickly go through this. So I'm going to stack it and then do the image processing and rotation. You can see the final image here, which shows a lot of detail on the planet's surface, including the great red spot. And to show you that we know that that's actually the right place, I asked Wolfram Alpha to compute the position of the great red spot on the date that that image was, the date and time that image was taken. And hopefully we will get some results here. So you can see it's in the same position. And as a little aside, you can also see I actually took several sequences and you can see the planet's rotating. So Jupiter rotates once every 9 hours. So in between the time I took the first sequence and the second sequence, it had shifted over a little bit. And people with more patience and time than I have actually take movies of this and just show Jupiter rotating all the way around. So, any questions?